let's go ahead and get started. I'm Julia Matevosyan. I'm Chief Engineer at Energy Systems Integration Group, or ESIG. I want to welcome you all today for our 2022 ESIG monthly webinar series, and I'll give you a little bit of background on ESIG if you are not familiar. ESIG is a membership-based nonprofit organization providing our members with objective information, resources, and networking opportunities to support our path to energy transition. We do this through workshops, tutorials, webinars, blogs, working group and task force activities, and producing technical resources and materials. ESIG also serves in a leadership role with Global Power System Transformation Consortium, or GPST, whose mission is to bring together key actors to catalyze a rapid clean energy transition at unprecedented scope and speed. ESIG leads Pillar 1 of 5 pillars in GPST, which deals with research agenda for the system operators. More information on GPST can be found at www.globalpst.org. We are currently busy preparing for the virtual generation interconnection workshop, which will be held at 1 to 4 p.m. on August 9th through August 11th. And this workshop will focus on generation interconnection process, studies, modeling, and interconnection requirements. Further information about the workshop is available on our website at www.esig.energy under events. Our workshops and monthly webinars are open to everyone, so please feel free to register anytime on ESIG website. If you are new to ESIG, I strongly encourage you to follow up with us, and you'll like things you'll hear and will be pleasantly surprised. ESIG membership will give you an opportunity to participate actively in all our working groups and task force activities. You can find us on web at www.esig.energy, as well as on LinkedIn, Facebook, Twitter, and YouTube. Okay, a few logistical matters before we get started. First of all, phones will be muted for the duration of the webinar to avoid unnecessary distraction. For the Q&A, we'll be using Slido platform. To ask your questions, please go to slido.com and enter ESIG27 as an event code. The instructions for these are also now provided at the bottom of the screen. You can use thumbs up button next to each question to cast your vote to help prioritize questions that are already submitted, or submit your own. We plan to save 10-15 minutes for Q&A at the end and then wrap up at the top of the hour. An email with link will be provided once the video file has been posted. The link to the recording and slides will also be posted on the event page. We also plan to provide short responses to all unanswered questions after the webinar, so please don't be afraid to post your question through Slido. All right, so today's topic will be Hawaiian Electric Company plans for meeting clean energy targets and the role of grid-forming inverters. And we are very fortunate to have Lee Yu and Ken Aramaki here with us today. Lee Yu is a manager of transmission planning at HECO, leading the team that performs near and long-term planning studies to support HECO in its transition to 100% renewable energy. In the past 10 years, he has been working on both transmission and distribution planning, DER, interconnection studies, both steady state and transient planning modeling and studies. He holds a PhD from Polytechnic Institute of New York and University, and he's an active member of IEEE and NERC working groups. Ken Aramaki is the Director of Transmission, Distribution, and Interconnection Planning at HECO. In his role, he leads a team that plans for the future of the transmission and distribution systems as increasing levels of renewable inverter-based resources are added to the grid. While at HECO, Ken held various positions in engineering, project management, and planning and technology. He holds Bachelor's of Science in Electrical Engineering from University of Portland and MBA from University of Hawaii at Manoa. Following Charlie's tradition, I actually went ahead and checked our connections on LinkedIn, and I'm happy to report that with Lee and Ken, we have 85 common connections in total. working with many of the same people over the years. I actually met Lee at our ESIG grid forming workshop that we held in June, and I've seen Ken at general meeting last week during a super session on grid forming inverters. So just a short reminder, once again, use Slido for questions. Event code is ESIG27 to ask your questions. And without any further ado, let's go ahead and get started. Lee, Ken, go ahead.
Thank you for that introduction. Aloha, everyone. And can you see my screen?
Yes.
Yeah, okay. Aloha, everyone. Good morning or good afternoon. And thank you, Julia and ESIG, for providing this platform. And to everyone who have joined us. My name is Ken Aramaki. I'm the Director of Transmission, Distribution, and Interconnection Planning at Hawaiian Electric. And today, Lee and I will be covering our company's plans for meeting our clean energy targets, and specifically the role that grid farming plays in this future resource mix. So the agenda, I'll be covering the first two items, which is a general overview of the company, as well as our near-term renewable plan. And then Lee will go into the details of the system stability analysis, which is currently in draft form. And I will come back to talk about the action items that we'll pursue coming out of those studies and analyses. In a lot of our presentations, we like to start off with this graphic. This is a reminder for us, as well as everyone else, that we're 2,500 miles away from California. We don't have an interconnection to the mainland grid. And specifically for our company, Hawaiian Electric operates 5 separate island grids, and those 5 separate island grids are also not interconnected together, and they all have their unique characteristics and challenges. The issues that will be presented today do not currently apply to the mainland, and I confirmed that with numerous discussions during general meeting last week. And these issues may not actually be seen for probably years, maybe even decades to come. However, we hope that you find this somewhat enlightening and insightful, and maybe some of this knowledge that we share today can help mitigate similar issues, or even spark ideas or solutions as an industry as a whole, and can help each other move towards these decarbonized systems. For Hawaiian Electric, these are some of our key 2021, I guess, results or highlights. Our renewable portfolio standard across the 5 islands was at 38%. So some islands have a higher RPS, some a little bit lower. But other things to point out is that we have about 1 gigawatt of nameplate solar capacity already on the system. And in last year, what is unique to our system as well is that 91%, on this bottom right, 91% of rooftop solar that was installed last year was also paired with battery storage. Late last year, Hawaiian Electric announced its climate goals, which is to reduce carbon emissions by 70% by 2030 and 100% by 2045 compared to 2005 levels. So the next few slides will kind of talk about how we're going to get, or how we plan to get to our 2030 target. So how will we get there? It's going to be a combination of actions. And in particular for this presentation, we'll be replacing fossil fuel units with utility scale and customer-sited renewable energy. With the customer-sited resources already in place, which is about a gigawatt, we do plan to increase the total number of systems by about 50% by 2030. In addition to that, we have plans for increasing the utility scale renewable capacity by about 1 gigawatt. So all of these new resources are essentially going to displace the fossil fuel synchronous machine units that we have on the system. This is a high-level overview of our near-term renewable plan. So what we call our near-term plan, generally in the 2027 to 2033 timeframe, we are doing what we call a stage 3 renewable variable procurement. And so that's within stage 3 is when we're going to try to procure a lot of utility scale resources. And then in addition to that, there's a lot of DER that's going to be coming onto the system. So the Hawaiian Electric system comprises of 5 islands. And so just to put into context, the 2 islands on the top left, which are Kauai and Niihau, Hawaiian Electric does not, it's not part of Hawaiian Electric's service territory. For Oahu, Oahu is our main, our largest service area by capita and demand. There are 309,000 customers. Peak demand is around 1.1 gigawatts. And to serve this load, we currently have 1.8 gigawatts of firm and about 1 gigawatt of a combination of utility scale and customer sited renewable resources. And in our stage 3 procurement, we're going to be seeking 475 gigawatt hours of variable renewable energy and about 500 to 700 megawatts of firm renewable energy to displace the existing fossil fuel firm resources. In addition, DER is anticipated to increase or forecasted to increase by approximately 220 megawatts or about 30% of capacity. On Maui, the Maui County consists of essentially 3 islands, Maui, Molokai, and Lanai. And those systems, the total peak demand is around 200 megawatts. We're seeking 180 gigawatt hours of variable resources in our stage 3, as well as around 40 megawatts of firm. This is for Maui Island, or the island of Maui. And DER is anticipated to increase about 55 megawatts, or about 39%. And on Hawaii Island, which is the largest island, but still the peak demand is around 200 megawatts. For that island, we're seeking 325 gigawatt hours of variable renewable energy, around 65 megawatts of capacity from firm or variable resources, as well as an increase of about 43% of DER nameplate capacity. The main takeaway of this slide is that in the next 5 to 8-ish years, we're going to be, we plan to add a large amount of inverter-based resources. We don't know where they are specifically going to be located. We don't know what the sizes are specifically going to be, but these are our target goals. And basically, without spoiling too much of Lee's portion of the presentation, the findings in the study focuses on the impact of inverter-based resources. And so what we do find is there are risks associated with the current inverter-based resources already on the system. Those are the grid following resources, as well as the DER resources. But we also look towards solutions to address those risks. So, and we'll get into that in our action plans. Excuse me. This next slide just shows a breakdown, of the DER that we have on the system. So I mentioned we have about over 1 gigawatt of DER across the islands. And this just shows that around 75%, which are the green ones, 75% of those DERs are generally exporting systems. The remaining 25% or so either do not get compensated for export, but they also have the ability to export, or are not allowed to export at all. Okay, and then before, this is my last slide before going to Lee's part. So, but before diving into the technical part of the presentation, we wanted to give a kind of a shout out to these industry heavyweights or titans. Many of you have seen these names, especially on these meetings. And as part of the Hawaiian Electric integrated grid planning process, we have a technical advisory panel. And this technical advisory panel helps pressure test our studies, our methodologies, our analyses. They also help provide guidance from their perspective and respective backgrounds. So Andy from NREL, Debbie from eSig, Matt from Telos, Dana and Vishal from SCE, and Deepak. Much thanks to all of them for helping us get to this point. And then also our key consultant for the stability analysis was electronics. So thanks to Andy and Lucas and the rest of the team for that. And in terms of vendor, we also really want to thank the vendor support for this, because we know it's hard, generally hard for vendors to provide as much information as we ask for. But Tesla and SMA have been great support for the analyses that we have completed. Okay, so with that, handing it over to Lee, who is our transmission planning manager. He'll provide details of our stability study. And the stability study wasn't done just kind of in a focused box. It was a cross-functional effort, and a key component of that was getting input and collaboration from our operations areas as well. Okay, so Lee.
You can. Thank you, Julia and eSig, for this great opportunity. From last summer to beginning of this summer, we performed our 2021 system stability study. This study is on top of stage 2 system-wide EMT study. I guess many of you may already read that report prepared by electronics team. On top of that system-wide study, target year at 2022 and 2023, we look 5 or 6 years ahead of that time frame, looking into the scenario that with more DER online and also load increase, and seeing in the near term what kind of the system stability needs. So this slide shows a high-level flow chart for this stability study methodology. We have assumption preparation part, which based on the past study and company's high-level resource plan, and generating the starting point assumption. And then we have the dispatch scenario preparation part, basically taking the production simulation, hourly data, identifying the future important dispatch for the study, also working with system operations to create the final dispatch of interest for the study, as well as sensitivities. And then we put into the simulation analysis. And after that, we generate conclusion recommendations to address system stability needs or capacity needs. And if necessary, we're going to feedback this mitigation or recommendation conclusion to the resource planning, start a new iteration of the resource planning model update. Next slide, please. So this slide shows an example of what kind of dispatch we look into the near-term future. This is left-hand side is the as the figure shows the started year Oahu system, 8760 hours production simulation data. So vertical axis shows the rotating machine generation megawatt, and the horizontal axis shows the inverter-based renewable generation, which including the grid scale IBR generation and distribution level DER generation. Basically, the red dot shows and also red triangle shows the studied dispatch, and also this dashed line shows the percentage of the renewable or percentage of the IBR in the studied system. Basically, we identify the dispatch with all different level of renewable or inverter-based renewable generation percentage, and we look into all those scenarios and identifying the stability risk. An example of generation profile in all this studied dispatch is shown on the right side of the slides. So this one is kind of like the dispatch with very high generation of the inverter-based resource. So we can see around 58% of the generation coming from distribution level, the DER side, and system only have 15% of the generation from rotating machine, and remaining part are from wind, existing solar, stage 1 procurement projects, which can only do the GFLs so far, and then stage 2 GFM projects. Next slide, please. In this study, we first time used the hybrid simulation process, which basically use PSC simulation as a screening tool to identify which case or which scenario, which contingency we need to put into the PSCAD running island-wide full model simulation. Yes, so for the PSCAD simulation, it's really time consuming for us. It takes around 10 to 14 hours to run one contingency. For PSC simulation, it's definitely way faster, but we do have some issues such so far we do not get really good PSC GFM OEM model, and also we see that there are certain risk or certain stability phenomena that we cannot see from PSC, but we have to rely on the EMT simulation. So on top of the base case study, which basically focusing on the planning event, such as the NERC TPL standard defined planning event, we also look into specific topics relating with the system stability, such as determine if we need synchronous condenser, determine how the DER moment cessation impacting the system, determine if we need more frequency response resource in the system, and also look into possible system oscillation scenarios. Next slide, please. So from this slides, I'll talk about some really important findings we see from this stability study. Among all the system stability risk, I would say the number one risk caused by the DER, and among all the DER risk, probably this system-wide DER moment cessation is the most critical one. Left-hand side shows a very famous plot from NERC guideline regarding the illustration of the IBR moment cessation. We use these curves, and which are Rule 14H, the tariff technical requirement of DER, as well as the inverter test result to come up all the DER moment cessation assumption for the study. So in our system, so far we have three types of DER: P1, P2. They are pre-2016 DER. Most of them are using legacy inverter, which complies with 1547-2003, that old version, interconnection standard. For the post-2016, we have our own source requirement document in our tariff. So in that tariff, we require that the moment of cessation under voltage limit for the DER should be no higher than 0.5 per unit. And so we put 0.5 per unit as a limit in the study assumption, in the modeling assumption. However, for the legacy pre-2016 DER, we did not have that requirement in our standard. And so far, we don't know exactly what their moment cessation under voltage limit. So via the inverter test, we are sure that probably 0.45, this kind of the limit is a really good estimation. So we use 0.45 as under voltage blocking limit or moment cessation limit for the Lex DER modeling. We use the latest 1547-2018 standard as a base to estimate the DER moment of cessation recovery ramp rate, which is number 4 here shows in this slide. Use that as an assumption for the ramp rate limit when DER recovering from moment of cessation, and also we use that standard to assume the recovery delay in this model. So we put all this parameter in our PSCAD model, in our single phase DER model, in our system-wide PSCAD simulation, and we see how DER moment of cessation affect our system stability. Next slide, please. So this is an example of what we've seen from PSCAD simulation about how DER moment of cessation affect the system stability. The top plot is system voltages. This is for our main system, our Oahu system. So we simulate a transmission level fault, and that fault lasts for 5 cycles. And after 5 cycles, fault get cleared, voltage start recovery. In the middle figure of this slide, you will see the DER total megawatt power generation. So we clearly see that after fault immediate recovery, around to 0.8 per unit, after fault get cleared, DER power start gradually recovering, which takes time. However, we know that system load, big chunk of load could recovery along with the voltage recovery. So it does not behave as a DER recovery. So during the DER recovery, we do see there's a big imbalance between power and demand. So that imbalance causes our frequency start decline, which you can see in the lower plot of this slide, because our system also already has a low physical inertia, and because of missing this big chunk of DER generation, frequency can decline very fast to around 57, 58 Hertz, which triggered 2 to 3 stages of unfixed load shedding. And that's why in the middle figure, you can see that the DER generation, after it reached the top, start reduced in that green curve. So that basically means DER gets shed in the unfixed load shedding. And because of the unfixed load shedding and remaining thermal generation, ramping up the generation, the system frequency gets stabilized and then gradually safe to close to 60 Hertz. Next slide, please. Besides system-wide DER moment cessation, we also see the potential risk of system-wide DER tripping. I want to mention that our system, comparing to mainland system, footprint is really small. So that basically means everywhere in the transmission level, when we have a fault, especially 3-phase to ground fault without any fault impedance, basically the whole system will see this fault. The whole system will experience very low voltages, and that will trigger DER momentary cessation. If that low voltage lasts for a certain time, then we're going to see system-wide DER tripping. So in our tariff, we have for the post 2016 DER, we have 0.5 per unit under voltage trip as minimum. We can accept the 0.5 second clearing time, and meanwhile we have zone 2 tripping in our transmission level fault. So that clearing time can also last to 0.5 seconds. So that basically means if there's a fault on transmission system and the clearing lasts 0.5 seconds, then we're going to see large chunk of DER get tripped because of the undervoltage issue. And right hand side, this two figures shows this, demonstrate this example. So basically, this is for Maui system. When you have a transmission level fault, last of 0.5 seconds, that can cause more than 100 megawatt DER tripping out of total around 120 or 130 megawatt DER generation. So once we have that big generation gap, we're going to need some generation immediate response to that gap and stabilize the system frequency. Another thing is that we frequently see there are many scenarios in our planning event simulation that system frequency change can be very fast. I think that's reasonable when we have very low physical inertial, when we have a lot of DER. That roll off in the simulation for the 0.1 second time frame, we can see it can range from 1 hertz per second to 6 hertz per second. So that basically means current 1547-2018 category 3 DER roll-off write-through requirement, which is 3 hertz per second, may not good enough for us. Also, this is something new, and we really have very limited knowledge regarding the roll-off write-through of the DER. So we don't actually model this thing in our system-wide model, and we are currently working with DER OEM, sending out a survey to them. I think Ken gonna mention that later, and also meanwhile working with AMRail testing inverter, make sure we have better knowledge regarding DER roll-off write-through capability, and then putting that into our planning model. Next slide, please. With the higher and higher penetration of the DER in our distribution side, we also see that it start reduce the effectiveness of our under-fixed load shedding system. So under-fixed load shedding system is still really important tool for our system to stabilize the frequency as a last resort. And to address that issue, we already have Hawaii Island system that are currently using dynamic under-fixed load shedding, which actively looking into the system available net load that can be used as a load shedding for stabilizer frequency. Also in our Maui Island system, we are kind of like adopting the dynamic under-fixed load shedding right now. And for Oahu system, so far we're still using static under-fixed load shedding system. And in our system stability study for extreme scenario, we do see that originally we targeted like under-fixed load shedding system with around 300 megawatt load can be used for shedding, and after assuming all the DER forecast can be realized in the future years, we only got around 80 megawatt net load in this toolbox. So we are currently addressing this issue now. Under commission's order, we're doing long-term under-fixed load shedding roadmap study right now, and we also have a plan to convert Oahu's static under-fixed load shedding scheme to dynamic one. Next slide, please. After about all this thing about the DER findings about the DER, we also see some risk regarding the existing grid scale solar IBR plants. So far, we have around 180 megawatt contract capacity for grid scale solar IBR plant in our Oahu system. They are transmission level interconnected and sub-transmission level interconnected. All of them are GFL control, and all of them we have vendor OEM inverter PSC model and PSCAD model. 2 years ago, we have a system event, a fault happened on the transmission level, and from that event investigation, we see almost all this, none of this IBR plant in existing grid scale IBR plant can provide grid stability support. So I will show some DFR trace in the next slides. Also, in the planning study, we see that there's a potential risk of instantaneous tripping because of the either zero time delay voltage tripping or frequency tripping. I think this is similar as what NERC find out from the mainland large-scale PV plant tripping report. From those model we put into the study, we see very different results. When we simulated the same event, we see many of them provide false positive simulation results, which means in the planning model, we still provide a really good system stability support. So that is something that we should really avoid in the current procurement and the future procurement. Next slide, please. This is a slide shows the DFR data we extracted from the system level event happened 2 years ago. Left-hand side, two plot shows high speed recording for one specific solar IBR plant. So you can see that the upper plot shows voltages, lower plot shows instantaneous current and the frequency. And system event happened around 0 second, and the fault lasts around 4 cycles, and which dragged the system level voltage around 0.4 per unit. So after that, fault get cleared, voltage immediately restored to 0.8 per unit, and then gradually restored to 1 per unit within 0.4 seconds. And during the fault, we can see the IBR basically going to momentary cessation mode. And after fault get cleared, it's still in the momentary cessation mode lasts for around 1 cycle to 2 cycles. After that, IBR start trying to increase current. However, something happens, then it make IBR gave up that attempt, and then we see very minimum current output from the IBR around that 0.2 second time, and then after that the IBR tried once more time and still failed. So in this 0.5 second time frame, basically we start seeing frequency started drop to around 59.6 hertz. But during this whole process, basically this IBR plant does not show any support. Using slow speed recording data, we can look into all 6 plants in our system performance during this event. Basically, from 0 second when fault happened to 1 second, none of them shows any support to the system on the frequency event. At that time, at around 1 second, system frequency already dropped to around 59.4 hertz. So very close to the time that on the frequency event is going to trip system DER. After 1 second, basically most of the IBR plant going to very minimum output active power, and the frequency continue drop. The nadir reached 58.7 hertz, and a lot of legacy DER got tripped. And two stage of unfrequency load shedding get triggered. After that, frequency get stabilized and start increase, and also or the rotating machine ramp up the generation, and then frequency get saved. But we can tell from this whole 10-second data, yeah, very few IBR plant increased power generation a little bit, and many of them still up and down, and some of them cannot even return to the pre-event generation after 5 minutes. Next slide, please. So with all these issues from the system stability study, we do see that stage 2 grid forming projects can be a really good mitigation solution, or can provide a lot of stability support to save those lost active power to make sure stabilize the frequency. In the bottom two plot, it's just a comparison between the stage 2 projects when they're in grid following way and when they are operate in grid forming way. So left-hand side plot, the green curve shows the older stage 2 projects power generation when they're in the GFL way, and we can see that the power can change from pre-event 70 megawatt around to 280 megawatt. For the same contingency event, when we put in the PSCAN around enable GFM function, we can see that it can change power from 80 megawatt to around 460 megawatt. So way more powerful than GFL response, and also much faster, much stable, and much responsive. After all this study, we revised our GFM function requirement in our standard PPA contract. Basically, we put the GFM function requirement in more detailed way. So we want that this storage GFM function should be relying on the internal voltage reference instead of the measurement of the POI, should be able to immediate response to system event, provide system stability, and work on very weak grid and even no grid condition, because we believe our grid is going to be weaker and weaker because we have to replace certain fossil generation. And also self-energization and black start is also important function for us in our storage grid forming requirement. Next slide, please. This one, I think, is really important. I presented this one in the general meeting a couple weeks ago, and a lot of OEM reached out to me to ask for clarification. I think, yes, I need to make a clarification here. This short-term on current capability is equivalent important for us as the GFM control itself. So we use this equation to quantify a design how much short-term or current capability it has. So we require 1.6 per unit for battery inverter. This is only for the battery inverter and for at least 5 seconds. There are folks approached me during the general meeting asking if this also apply for the wind or other technology. Yeah, I would say, yeah, so far this is only for the battery inverter. And we also look at the bid received during the stage 1 and stage 2 projects. We already see many bids can reach this 1.6 per unit requirement. Yeah, next slide, please. This slide basically summarize what we see from our system stability study for system stability from only this perspective, and for our system, how we categorize all those grid resource, how they contribute to system stability. We do believe with good short-term or current capability, with tuned control, the GFM projects stage 2 projects, they can provide really good performance for our system stability to mitigate all those risks we see in our system. And we believe synchronous condenser can do so, but the only reason that we put GFM is more toward improved stability side than synchronous generator is that we believe the GFM can even overcome the disadvantage of the synchronous generator swing that part. Of course, we see that uncontrolled DER is a big risk for our system stability. That's why we place it as the most left-hand side, means that impact stability most. And regarding the condenser, I think maybe from the slides we can say, or from the study we can see that missing power imbalance, especially active power imbalance, so far is our near-term concern due to the system characteristics. So far we see, yeah, that is way more important than the voltage wide issue. So that's why we put synchronous condenser as well as a StatCom in that position. And I believe if there are new technologies such as StatCom plus, the super cap with the so-called GFM StatCom, or even existing synchronous condenser plus flywheel or plus battery, definitely they can do much better for improved system stability. Yeah, for the DER, if we can enable the control, make it can be curtailed during a certain time frame for the system operation needs, we believe their impact to system stability can be improved. Okay. Yeah. So next slide is yours, right? Yeah.
Yeah. Okay. Thanks, Lee. Okay, so to round out this presentation, and we'll try to leave some time for Q&A. Just going over a few slides with the recommendation and actions from the stability analysis. So first, we're going to continue to procure grid-forming inverter-based resources for our utility scale resources. So for all future battery or storage inverters, only accept grid-forming control with that short-term overcurrent capability requirement that Lee went over. Right now, it's a requirement for storage inverters. We do understand that there's been advancements in other types of inverters. So, we kind of lean on the industry to understand and know where that's headed for, like, PV only or wind only resources. In terms of DER, we are working to close some of the unknown gaps. So specifically figuring out how they respond to low voltage events and high rate of change of frequency situations. This will help us calibrate our models and simulations for the DER that's already been implemented, and probably just the DER that's going to be implemented in the near term. For future DER, we do see that there's going to be a need to see how far we can take the functions of the DER. And just like when NEM was kind of growing at exponential rates, the requirements for our system is going to continue to be higher than the standards and the minimums that are being set, or the minimums being set within the standards. Also regarding, under frequency load shedding, DER is generally interconnected to the distribution system, and it makes it difficult to maintain the effectiveness of the current UFLS scheme. So migrating to a dynamic UFLS system, and I did see a question about that, so attempt to address that now. Dynamic under frequency load shed system, basically UFLS, currently a static system just trigger at certain triggers of frequency drops certain feeders or distribution circuits. But a dynamic one takes actual measurements from the field maybe every 15 minutes or so to know what the net load on that circuit is to determine which circuits are actually dropped in the event of an under-frequency event. And then also, because the under-frequency load shed, you want to drop load, what we need to do in the future is understand what types of loads are out there or are going to be implemented, and see how we can address the UFLS functionality with these new loads. So for example, EV chargers might be a good way to add to the under-frequency load shed scheme, where in times of need for dropping load, maybe we can drop EV chargers for a short duration until the system can recover. Okay, and while grid forming is shown to be supportive in the simulations, we need to be able to confirm that the performance is actually meeting what the models show. So we're going to continue to utilize digital fault recorders to capture the performance of the grid forming IBRs during system events, and using that information to calibrate our models and simulations for future, I guess, models and simulations. And while the simulations are not perfect, they still provide a peek into what that future is going to look like, or what that future performance is going to look like for these plants. And then in terms of planning studies, we did find limitations on the positive sequence simulation software. One of the limitations is that we don't have OEM specific. Generally, we don't have OEM specific models, grid forming models that can be used in the PSSE models. And also the PSSE wasn't able to capture all the issues on this really low or inertial-less system. And EMT modeling gives more confidence into identifying the issues. So that's why we did focus on, we used PSSE PSSE as a screening tool to see where the risk events are. And then we used the EMT simulation to look at those high risk types of scenarios. And this is because EMT simulation, it takes much more time to do versus a positive sequence simulation. And going forward, we have to continue to grow our internal resources to be able to execute these EMT simulations. So that's going to require much more training, better software, and then also higher end workstations. The simulation runtime is much longer, and even though computers get faster and faster, what we do see is that the simulations are going to continue to gain in complexity as well, while computing power improves. And that's because there's all kinds of stuff that can be modeled and or should be modeled to look at what the future is going to be. So in conclusion, our grids continue to evolve very quickly. We don't have a crystal ball. We're trying to figure out what the future is going to look like and study it and see where the risks are and try to develop implementable action plans. What we do know from the studies that we have performed is that grid forming is critical, especially for us and probably other areas that have 100% renewable plan. The grid following alone will not get us there. We do need to address the risks of the existing inverter-based resources as well as future DERs on the system, those being added in the near term. And the other thing is we don't know what we don't know yet. So we may be just scratching the surface of future risks. We are putting a lot of faith in grid forming functionality in the support of the system, but there could be something that is just not shown in the models that could happen when we implement these at scale. And also, being a small state, a small company, small utility, we really rely on our stakeholders in the industry to help push everyone to get to this decarbonized future. That's it. Thank you. Thank you all for your time.
Thank you, Kenley. Very interesting presentation. So we don't have much time for questions, but I hope we can get at least to some of them. The first question is, have DC links ever been considered between the islands?
There were studies that were done prior to my time, but yeah, I think those were looked at. There were high costs associated with it, and as well as environmental, cultural types of concerns.
Right. Next question is, can you elaborate more on screening criteria used in BSSC study to go to PSCAD?
The
Okay, this is the first time we're doing this. Still need a lot of lesson learned there. So far, we are looking into the scenario that cannot be solved in the PSC or has really large violation in the PSC, putting those scenarios into PSCAD and run. For the scenario that the PSC study shows good and no issues, we normally will not look into checking them in the PSCAD. But I would say that planning experience, engineering experience is also really important input to select what kind of scenario put into the PSCAD run. For example, in our Maui Island, we have maybe more than 300 PSC contingency put into the list. We got around 200 contingency cannot be solved. So there's no way we can put a 200 contingency into PSCAD.
Yeah. Okay. Right. Next question is, has Hawaii Grid experienced any inertia issues so far? What mitigation strategy is being considered or utilized to handle it right now?
Lee, you want to take down?
Okay, yeah, I think physical inertia issue, we see the only way to do this 100% renewable is we can continue losing physical inertia. So that's unstoppable. In order to compensate that, we have to rely on faster control to mitigate this transient power imbalance issue.
Mm-hmm. But say if currently you're running into this issue, what do you do today ahead of grid forming inverters being deployed?
Yes, that's a really good solution so far. Yeah, so we're gonna put that into our procurement. So far, we're only requiring the grid forming inverter and also this 1.6 per unit with grid forming control. This is also helping us to quickly respond to the under frequency event. Yeah.
All right. Can you please explain how DR rock-off trip settings have been modeled? DR rock-off tripping has been observed in UK August 2019 event.
So far, we do not have a model that in our model. We're still working on it.
Mm-hmm. So you're basically just looking at rock-off that happens in the event and kind of using engineering judgment, thinking
Yes.
how much DR will trip offline because of that.
Yeah, something like that. Yeah.
All right. You've mentioned the importance of black start capability for HECO. How are DR managed during system restoration to ensure a minimum load is maintained?
I think that probably is more related with the seesaw upside. We can reach out to our system operator and then maybe put it back.
Yeah, we can link that question on. You can address once you get all the rest of the questions. I think then the next one you've answered already. What are the current firm generation resources? There were like a couple of questions about firm generation resources that you have currently, and if you're going to require any firm generation resources going forward. So maybe we can there were 3 questions on that, I think. On slide 7, they say, but we can just respond.
Sure. Yeah, our current firm resources are fossil fuel resources, both sulfur, fuel oil. They are aging, so we do anticipate to start, retiring those units or is retirement the word? Retirement may not be the word, but to reduce the use of them. And then also with stage 3, there are plans to add some firm resources as well, firm renewable resources.
Mm-hmm. And firm renewable resources, what would that be?
Biodiesel, biomass. Yep.
All right, I see. Thank you. I think I'll go ahead for just one and we'll wrap up. There was one interesting one. Please comment on the portion of your study results, lessons, and how it can be applicable to larger grids when the grid reaches comparable penetration levels.
I think the stuff from our study that may apply is essentially what we're finding is that the system is going to get faster and faster, right? So we need resources that can respond faster than the issue happens, or maintains its output through these like really transient events. So probably as other areas lose inertia, or as their systems get faster and faster, some of these learnings can be used for theirs.
Mm-hmm.
Yeah, also, like some emerging issue, like coordination between the power plant controller with inverters and the inverter DC side, all these kind of things. I think they also applied on the mainnet system. Yeah.
All right. Okay, we are slightly over top of the hour, so I'm going to wrap up. I want to thank Lee and Ken for really informative presentation, and for audience for your attention and for great questions. As I mentioned earlier, an email will go out once the video file has been posted, and we'll answer all the questions that we didn't get to and get them posted quickly as well. There was a question about slides, and slides will also be posted on the event page. So once you get the email about recording, go ahead and check that event page and see the slides. As I mentioned in the beginning, I would like to invite you to the upcoming virtual workshop on generation interconnection in August 9th through 11th. The next ESIG webinar on market design concepts for evolving power systems will be held on August 23rd, and it will feature Bethany Fru and Yinong Sun from National Renewable Energy Lab. Further information of all of our webinars and meetings can be found on our website at www.esig.energy under events, and our newsletters and informational emails also contain this information, and you're all invited to attend. Lee, Ken, thank you once again for a very timely and informative webinar, and thank you all for your interest. We look forward to seeing you again in the near future. In the meantime, everyone, take care, stay safe, and thanks for your participation. See you soon. Bye.
Thank you all. Thank you.